Okay, are we still recording? Now I'm worried that went away. Oh, that wasn't it. That's it. Okay, I think we're good. I think we're good. All right, so here we go. How far did we get yesterday, guys? Did we knock out all of these? Okay, so walk me through what happened on this last example, everybody. That big square root, how did we come up with the 15? 15 is the square root of 225. Now I'm thinking with these last two examples, everybody, we learned something right there. If you want to take the square root of a monomial, a variable raised to a power, what do you do with your exponent? Just cut it in half, right, guys? So the square root of a to the 10th became a to the 5th. There we go. And the square root of b to the 16th became b to the 8th. That, I think, is about as far as we got yesterday. We were messing around with a couple of rules right here, but we were just starting to get into this, and this is where we're going to pick it up here today. All right, so the square root of 50. I think I said this yesterday. What's a smart middle school going to tell you about the square root of 50? They're going to say there isn't one. And their reasoning, I get it, their reasoning is that there is no number that can be multiplied by itself that will give you 50. Is there one? You guys are a little sharper than that. There is one, okay? But it's not what nice kind of number. It's not a whole number. In fact, it's not even a fraction or a decimal that works out nicely, everybody. It's this whole new category of numbers called irrational numbers, which you guys are going to get a little bit more familiar with next year in Algebra 2. You guys already know one irrational number. Does anybody know what it is? It's not zero, it's pi. That's right. What makes a number irrational is that there is no nice, clean decimal or fraction that expresses the value of that number properly. Isn't pi 3.14? No, it's not. 3.14 is a pretty decent approximation for pi, but that's not the exact number. And there is no nice exact number. If there were, we would tell you guys this is what pi equals. Well, the square root of 50 is kind of the same way, everybody. So we're going to talk about how to handle this. But before we go any further, there's a category or a group of numbers over here that we better get familiar with, everybody. And I can't remember if this phrase got brought up yesterday or not. I think it did. We're going to make a quick list of our perfect squares. Have we seen a perfect square here, guys, in what we were talking about yesterday? Like what? 49 is a perfect square? 144? 225, and the 25 and the 36. All of those numbers were perfect squares. So with that in mind, I think you guys know what they are. Let me ask you a question. First of all, how many perfect squares are there? How many is a lot? Infinitely many. So I have good news. We're not going to write down all of them, okay? But we are going to write down probably about the first 16 of them, if I'm not mistaken, the ones that are going to be useful, everybody. Do we know what the smallest perfect square is? Not 4, not 2, not 1, 0. 0 is a perfect square, everybody, because there is a whole number multiplied by itself that equals 0. And what is that whole number? Yeah, 0 squared is equal to 0, and that makes 0 a perfect square. Now, you guys told me the next biggest perfect square is 1. What is the square root of 1? Just 1. Now, I got a little worried here. Some of you said 2 a minute ago. Is 2 a perfect square? No, there's no whole number or no rational number times itself that equals 2. What's the next biggest one then after 1? That's going to be a 4. Good. Do one more and then I'll stop for a second. The next biggest one after 4? Okay. Now, there's kind of a quiet among you guys right here, which is not unusual. But let's talk about why. That quiet tells me that we don't entirely know where these numbers come from. And some of you are a little confused right now and you're just thinking that I'm pulling numbers out of thin air. There's a reason these numbers are perfect squares. How do we get 0, guys? By squaring what number? So this is 0 squared. This is 1 squared. 4 is 2 squared. And 9 is 3 squared. So this is your pattern. You guys don't have to write this part down, but 0 squared is 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9. So now I'm hoping you guys are going to go a little faster. To get the next perfect square, what number are we going to square? 4, and 4 squared is 16. So that's our fifth perfect square. What's next? Yep, 5 squared is 25. Keep going. 36, that's 6 squared. 49, that's 7 squared. 64 is going to be 8 squared. I'm going to go to the top of the next column here. After that, 81, 10 squared is 100. Do we know 11 squared? 121. There we go. 13 squared. 169. 14 squared. If you can remember this one right here, guys, 14 squared, you just switch around those last two digits right there, and the 14 squared is going to be a 196. So those two kind of go together. 15 squared, you told me yesterday, was 225, and that's really honestly about as far as you would need to go. Again, could we keep going? Sure. Anybody know 16 squared? 256. 17 squared? 289. 18 squared? 324. It goes on and on. And unless you're super cool, you don't have those memorized, and you probably don't need to, let me be honest. Okay? So everybody, those are the first 16 perfect squares. Again, there's an infinite number, but that's probably all we need to know. And where those come in handy, guys, is in this process right here of simplifying a radical for a number that's not a perfect square. So we're going to talk about what to do now with the square root of 50. And the very first thing we're going to do right here is we're going to split up that 50, everybody, into the product of two numbers. Now give me some numbers that multiply to 50. 5 and 10, 25 and 2, one more. 50 and 1. Now, which of those are we supposed to pick? Well, the only benefit to doing this and simplifying a radical is if you can find me a factor pair that contains a perfect square. So what I should have asked you guys is, instead of just give me two numbers that multiply to 50, do any of these red numbers on the right divide evenly into 50? Oh, 100 doesn't go into 50. 50 goes into 100. 25. So I'm going to make this square root of 50 the square root of 25 times 2. They don't both have to be perfect squares, you guys. They really only one of them has to be. All right? Now, the benefit to what we did right there is not immediately apparent. But do you guys remember yesterday when we wrote down these two properties over here, maybe high up on your notes? There's a third property I want you to write down too. And again, I think you learned this last year, but we haven't used it and you probably forgot it. One property of radicals is that the square root of a product, like the square root of a times b, can be broken up into two different square roots and multiplied together. So I can split this now into the square root of a multiplied by the square root of b. So that's a third property that we better have written down. And that's the one right there, guys, that we use to simplify radicals all of the time. All right, so one more time. The square root of a product can be split up into the product of two different square roots. Real quick kind of demonstration of that. Let me ask you guys a stupid question that I know you know the answer to already. What's the square root of 36, everybody? We all comfortable with that fact? The answer is 6. But if I felt like messing around with it, couldn't I split that 36 up into two factors? What perfect square divides evenly into 36? 9, right? 36 is the product of 9 times 4. Now, whoa. By dumb luck, 9 is a perfect square, and so is 4. So check this out, guys. If I use that property that we just wrote down, we can split this into the square root of 9 multiplied by the square root of 4. And this got easy here. What's the square root of 9? 3 times, what's the square root of 4? 2, and the 3 times 2 is going to give us 6. Wasn't that what you guys all told me a minute ago the answer was? Okay, so in an easy case like this, there's no benefit to doing what I did. But if this was a really big number, like 576 or 1024, a number that you might not recognize as a perfect square, that's the way you can kind of get that answer there without having to go through everything that long way. So with that in mind, We made this the square root of 25 times 2, and guess what we're going to do with that? I'll ask again. Guess what we're going to do with the square root of a product? We're going to split it into two different square roots, guys. So this becomes, So this becomes the square root of 25 multiplied by the square root of 2. And one of those numbers is a perfect square. Which one? 25. So right here, guys, what is the square root of 25? So that can be simplified to just make a 5. Unfortunately, 2 is not a perfect square. There is nothing we can do with that. So that just tags along, and we write this now as 5 multiplied by the square root of 2. Now, can we do anything else with the square root of 2? Does 2 have a perfect square factor that divides into it evenly other than 1, which doesn't help us at all? No. Actually, I should put a line right here, guys. 0 and 1 are perfect squares, but they don't help us at all when we're trying to simplify radicals. So because we've got this down, and anybody remember the R word for this number right here? The radicand. Good. Because the radicand doesn't contain any perfect square factors other than 1, this is in what we call simple radical form. And with simple radical form, everybody, that's as good as that's going to get, and that is your answer. Now, if you're wondering what it was that we just accomplished, okay, I'll try not to make this too long and boring of a story. 50 years ago, like when my dad was in college and he was doing engineering, do you think they had to do square roots for some of the problems they were solving? Yeah, they sure did. But guess what we have today that they didn't have in the 1960s? Well, they had crummy calculators, right? They would basically just add, subtract, multiply, and divide. So what they had instead were all these long tables in the back of their book that would tell you what the decimal approximation was. And people like my dad in 1960 or whenever he was in college, they used to have to memorize a couple of these radicals. And one of the things he had to know, just like you guys have to know that pi is roughly 3.14, he had to know that the square root of 2 was roughly 1.414. And what his crummy calculator in 1968 would do, Byron, is it would multiply 5 times, and then he would just type in 1.414, and that would get him a pretty decent approximation. Now, I'll be the first to admit with you guys here, unless we're talking about variables, okay, which are not in this problem, calculators today have made this skill much less important than it used to be. Now, all of you guys who listened to me at the beginning of the year and said, you know what, okay, I am going to buy that TI-30XS Multiview, this is the real payoff for it right here in Chapter 8. Because if I ask this calculator what the square root of 50 is, has anybody noticed this during the course of the year? This calculator for $15 will simplify radicals for you. Your phone calculator will not do this. Okay, if you type this into your phone calculator, it's going to give you the decimal approximation, which is 7.071, yada, 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 yada. Now, just to be clear here, guys, we haven't changed the value of the number. It was 50. We made it 5 root 2. If I wanted to know what 5 root 2 was, so 5 root 2 as a decimal, well, hitting enter doesn't do anything, but that's the number I get right there, guys, 7.071, blah, blah, blah. And if I check that against the square root of 50 and hit enter, I get the exact same thing. But my dad back in the day would have now multiplied 5 times, and they knew that the square root of 2 was about 1.414. Look at how close they get there, guys. 7.07. Okay, so that was a pretty good way of doing it back in the day. So if we have the multi-view calculator and the yellow ones that you guys borrow from me, that's what these are, this will do that for you. But it won't help you next year when variables get thrown into the mix. All right, let's do a couple more right here to get the hang of this. Square root of 24. All right, guys, is 24 a perfect square? It is not, but it might still be able to be simplified. So let's see what we can do. Looking back at our list of numbers over there on the side, do you guys see a perfect square that divides evenly into 24? I think it's just the 4 right there. I think that's the only one. So we break this up into the product of the square root of 4 times 6. What's the next step? split it apart, right? We make this the square root of 4 multiplied by the square root of 6, and one of those can be evaluated, everybody. What is the square root of 4? Just a 2, and then the root 6 just tags along on its own. Now make sure you're done. Are there any perfect squares that divide into 6 other than 1? Nope. So that's it, guys. 2 root 6, and that's our simplified version of the square root of 24. You guys want to try 72 on your own? Okay, go ahead, give it a second. Not going to give you long on this one. All right, let's keep going with that. Okay, so let's see where we're at. First thing we needed to do, guys, was to split this. What perfect square did you guys find that went into 72? How many people use 9? It'll work. Okay, so the 72 becomes 9 times 8. We split that up into the square root of 9 multiplied by the square root of 8, and then what'd you come up with next? 3 times the square root of 8. So how many people got that for their answer? Okay, I have good news and I have bad news. The good news is you have correctly simplified this radical. The bad news is you haven't gone far enough yet. The reason we're not done here, everybody, is because there is a perfect square in that list that divides evenly into 8. What is it? It's 4. So you guys don't need to erase anything that you did, but we just need to go a little bit further. I'm going to rewrite this now as 3 times the square root of 4 times 2. And then I'm going to split this. Bless you. 3 times the square root of 4 times the square root of 2. And what does the square root of 4 become? Careful now. Just plain 2, right? Once we evaluate the square root, we don't have to say square root again. So one more time, everybody. The square root of 4 is just 2. So this becomes 3 times 2 times the square root of 2. And we put the 3 and the 2 together to make a 6. We're multiplying there. 6 times the square root of 2. Now are we done? Are there any perfect squares that divide into 2 other than 1? Nope. So that's it. Now, guys, that was a two-step process. Did anybody take out a different perfect square, though, other than 9 at the very beginning of this problem? Alberto, say that again. Okay, good. What we really should be doing, you guys, isn't just looking for any perfect square. We really should be looking for the biggest perfect square. And here's something, Jack, we were talking about calculators a minute ago. This is something that unfortunately, when you have a calculator, you lose track of. Guys, what's the biggest number that divides evenly into 72? Kind of a trick question. 72. So in general, the biggest number that divides evenly into a number is that number itself. But let me ask you this now. This is a little harder. Do you guys know the second biggest number that divides evenly into 72? It's 36. And Austin, what's special about 36 compared to 72? True, not where I was going with that though. What's the biggest number that goes into 70 other than 70? 35. The biggest number that goes into 100 other than 100. You guys realize what you're telling me each time? It's half. So the biggest number that goes into a number other than that number itself is half of that number. So that's the first place you guys should start looking in your list. Okay, 72 is not a perfect square, and you should be thinking then, what's half of 72? 36. So look for 36, but don't think about any numbers bigger than that because they're not going to work. 36 ends up working. So what you could have done here, guys, is gone this route. The square root of 72 could have been broken up into the square root of 36 times 2. And now this would have been the square root of 36 times the square root of 2. And what is the square root of 36? 6. And the root 2 just tags along, and there's the same answer, which we got in half the time. Okay, so what have we learned there? You should always try to pull out which perfect square factor. the biggest one that you can. And that'll save you from having to do the same thing multiple times. All right, a couple more examples, then we're about done with this. This proves a point I was using just a second ago. 576. Now, this is a big number right here, and I wouldn't expect you guys just to know it. So, grab a calculator if you would real quick, all right, if you got one handy. Are there perfect squares that divide evenly into 576? Again, I wouldn't expect you just to know it because it's a big number. But if you go back to that list of perfect squares, start playing around with some of them. Byron? That wasn't a perfect square that was on the list, but I know where you're going with this. Any guesses, everybody? Anything that one of those red numbers might go into it? Hey, Taylor. Hey, quick question. Is there any chance that an odd number can divide into an even number? That one can happen. You got to be careful because an even can't go into an odd. That's fine right there, Taylor. What do you guys want to try? Pick one, maybe. 49. Okay. So what I would check real quick there, Austin, would be, okay, the number was 5. Let me clear that out. 576 divided by 49. Oh, that one didn't work. Let's try another one. 81. Nope, that one didn't work. Let's try another one. 64. Hey, that one worked. So, you're not going to guess right the first time, but keep going until you get one that gives you a whole number for your quotient. So, 576 can be broken up into 64 times 9. So let's write that down, everybody. So the square root of 576 becomes the square root of 64 times 9. What's our next step? Split it. This becomes the square root of 64 multiplied by the square root of 9, and we simplify what we can, everybody. The square root of 64 is 8. Now, usually, we're kind of done right here, but in this case, the square root of 9 is 3, and the 8 and the 3 multiply together to make 24. So what does that tell us, you guys, about 576? If its square root is a whole number. It's a perfect square. And Byron, I know that's what you saw in your calculator, right? If you just typed in, hey, what's the square root of 576? It, of course, is going to give you the answer right there. But for those of you who might be using your phone calculators for homework and you don't have that, or the older ones right there, the X2S, Lydia, this is a way you can do that. Just keep trying and see if you can get something to divide out, okay? All right, and I think I got one more to do with you here. Yeah, let's do this one. This is getting heavy here into the algebra, everybody. You'll see a lot of this next year. We're just going to do one of these for fun. Don't worry, this isn't going to show up here in much of the geometry that we do. All right, here we go. Is 500 a perfect square? Check it. Well, don't just type it in. It's not. Can anybody find me one of those red numbers that you should be able to just tell me immediately without checking your calculator goes into 500? 100, right? So 500 can be broken up into 100 times 5. Now, this is worth talking about, everybody. Do you guys remember yesterday we did 2 problems at the end of this list that had variables in there, right? Everybody, what was the square root of x to the 6th? X to the 3rd. So my question for you guys is x to the 6th the perfect square? Did it work out nicely? Then the answer is yes. What made this a perfect square? The exponent is even. Same thing with a to the 10th, same thing with b to the 16th. If your exponent is even, that monomial is a perfect square. Now, did that happen in this problem right here? Is x to the 5th the perfect square? It's not, because 5 is odd. Okay? But what we're going to do now, guys, is just like we did with the 500, we're going to try to split up x to the 5th into the product of 2 perfect squares. Everybody, what's the biggest even number smaller than 5? 4. So we're going to split x to the 5th up into x to the 4th multiplied by what? X to the 4th times what gives you x to the 5th? Just x to the 1st power, which we can just write as an x. Let's keep going. Is y to the 9th a perfect square? Oh, don't get fooled here, guys. I laid a trap for you. People say yes because 9 is a perfect square. But wait, let's go back. Why was x to the 5th not a perfect square? Because the exponent was odd. So is y to the 9th a perfect square? No, because the exponent is odd. So everybody, we multiply this now by, what's the biggest even number smaller than 9? 8. So we make this y to the 8th multiplied by just plain y to the 1st. So what this is, everybody, is a way of rewriting this with a whole bunch of perfect squares in there. We've got this thing down to 1, 2, 3, 4, 5, 6 factors. And now I'm going to show you guys a shortcut right here. I like to skip that second step. What I like to do at this point is just go through and circle all of my perfect squares. What's a perfect square in this mess? 100, x to the 4th, and y to the 8th. And what we're going to be doing, if you think about the way we did the last few, we separate those and we take the square roots of those perfect squares. So everybody, what is the square root of 100? So that gets pulled outside of the radical. That 100, we take the square root and it becomes a 10. What's the square root of x to the 4th? We cut the number in half and that becomes x squared. And what's the square root of y to the 8th? Y to the 4th. We just cut all those exponents in half, everybody. So the 100 got us the 10, the x to the 4th got us the x squared, and the y to the 8th got us the y to the 4th. But there are numbers that are trapped under the radical that we can't pull out because they're not perfect squares. What did we not bring out, everybody? A 5 times x times y. Do you guys see any perfect squares now that divide evenly into any of these numbers here? No? Then we're done. This is our answer, guys. 10x squared y to the 4th multiplied by the square root of 5 times x times y. Okay? Whew, good times. All right, that's where we're at, everybody. We are now ready finally to pick up the Pythagorean theorem, but with about 3 minutes left, I think we're going to kill it right there, and we're going to pick that up on Monday. Sound good to you guys? Okay, as the cool kids say, it's been real.